Danny Ruiz is going to be the chairman of the first session, so I give the floor to him.
Okay, thank you for all of you for being here today. My name is Daniel Ruiz. I have the pleasure to be the first chairman of this nice event. Nonsense to have more introduction rather than Pablo did. So let's go directly now to the talks. And the first talk that we have today in the morning is that Firat Guder. Firat Guder got his PhD, postdoc in George Whiteside's lab at Harvard University. Right now he's working at the Imperial College of London. And his main topic are design and fabrication of sensors and actuators. And specifically, the talk for today is going to be measuring and predicting soil nitrogen with point-of-view sensors and machine learning. Thank you.
Good morning, everyone. I will now share my screen. All right. Okay, I can see that you can see my screen. So yeah, it's a great pleasure to be here at this fantastic event. It's such a shame that I'm not able to attend in person, but hopefully in the future we'll have more opportunities. So today I will essentially talk to you about one of our most recent work, focusing on solving one of the biggest challenges in agriculture. That's the use of, or the overuse of fertilizers, and more specifically nitrogen fertilizers. And I'll go over the technology that we have developed that aims to tackle this problem. So everything that I will basically describe here is also published in one of our, again, recent publications. In fact, it came only online a few days ago in Nature Foods. So, you know, if you miss out something, do reach out to me to learn more about it. But furthermore, you could also have a look at the paper. All right, so, you know, if you go to a modern field today and then look at the way, you know, how crops are harvested and farmed, and compare it to a couple of decades ago, you will see that things haven't changed that much in agriculture. I mean, okay, the tractors have become clearly bigger and more sophisticated, and in some ways a little bit more automated. But we more or less do agriculture the same way as we have been doing, you know, nearly half a century ago, if not more. But what we have been kind of doing is that we have been just adding more and more and more additives to our crops, mainly to improve productivity. And one of these inputs into modern agriculture is the nitrogen fertilizer. In fact, this nutrient plays such an important role on society and the human civilization that, according to some estimates, if the synthetic nitrogen fertilizer was never introduced, the population of the world would probably be about half of what it is today, because this is the invention that really allowed mass production and large-scale production of various crops that require nitrogen as a source. So that's not able to fix its own nitrogen, essentially. So it's really, nitrogen fertilizer plays an important role. And the use of nitrogen fertilizers has increased 600% in the last 50 years. So we're just adding more and more and more and more nitrogen fertilizer into soil, just to hope that, you know, that we will never lose any yield because of the lack of nitrogen fertilizers. So, when if we take a step back and summarize the modern nitrogen or the synthetic nitrogen fertilizers of today, well, again, they're the most used soil additive, And wherever you go in the world, more or less, you will run into nitrogen fertilizers when basically growing crops and so on, because it's just such an important additive. Everybody's using it. And the problem with nitrogen fertilizer is that its application is poorly understood. So we don't necessarily know how much to add. And some of this knowledge of how much to add comes from the governments in the form of guidelines. So there will be some sort of a book, the one that's shown to the left here, that's passed on by the government or various agricultural associations to their members or to farmers, giving guidelines on how much to add, how much fertilizer to add, nitrogen fertilizer to add for what crop and so on. And some of it is just family know-how. People will be like, well, my great grandparents were, let's say, farming this land, and then which got passed on to my grandparents, and then they were using this much fertilizer. Obviously, if it's really way back, then it wouldn't be synthetic, but the equivalent of that. So it's kind of like a family know-how that's being passed on from generations to generations, even, and that's developed over the years. But it's because we really have a key lack of understanding of how much fertilizer to use across the globe. The use of nitrogen fertilizers varies significantly. For example, in China, 8 times more nitrogen fertilizer is used per hectare than, for example, Australia. So, and because we don't want to use any yields due to the lack of nitrogen in soil, excessive use is very, very common. And to combat this, we kind of really have one weapon, which is to use lab testing so that we can adjust the values. But people don't usually do this. And one of the reasons is because the nitrogen dynamics in the soil is relatively fast. And aside from that, lab testing is expensive, and in fact, in this work that we performed, we had we have run some lab testing ourselves, where we collected some samples and then sent it to a central lab for benchmarking and data collection. And this can take a couple of weeks. And our bill was very, very large at the end of this whole project, just our external lab testing. So because of these issues, lab testing is not performed commonly. So, and well, what happens if we use nitrogen more than that we need? Well, the excess nitrogen ends up in the ocean or in lakes and rivers. And because of excessive nitrogen, we run into problems such as the algal bloom, which it's shown here. We get basically a lot of algae, and which makes water hypoxic. So and then when the oxygen levels drop within water, essentially it becomes kind of like a tomb and a grave for the wildlife in it. So it really is a bad thing for the environment, because it destroys the ecosystem. So excess nitrogen is really bad for the environment as a whole. But if we're more pragmatic and say, well, let's just not care about the environment and then the effects on us, well, if you put excess nitrogen, meaning the nitrogen that you really don't use, you're actually burying money into soil that you could save otherwise. So because agriculture is already a very cutthroat business and the margins are very short, so using more than what we need is very, let's say, on optimum, because we're losing money by just, and fertilizer is expensive as it's tied to fossil fuels and so on. The prices fluctuate and etc. So usually we want to use just the right amount, nothing more and nothing less. So if we then now look at the main question, how much fertilizer do we need to add? So, well, we need to really know 2 things. First of all, what are the soil nitrogen levels right now? So if, here in the context of this work that I'm presenting, we're talking about nitrogen fertilizer. So we're mainly interested in soil nitrogen And again, nitrogen fertilizer being the most common additive. So what are the soil nitrogen levels now? And what will the levels be in the future? Because in key points in the future, the use of nitrogen will be will basically increase for the plant, and we want to make sure that during those times we have sufficient nitrogen in soil. But the main issue is that the fertilizers are added always at the beginning of each crop cycle. So before the seeds are sown, the fertilizer is added, and then the field is kind of left. So there really doesn't, there is not much happening in terms of fertilizer addition to the soil once the plants or the seeds have been sown. So we really kind of need to understand these two things so that we can adjust how much fertilizer we need to add. So we said, okay, well, can we measure the levels in soil now? So, well, when we looked at the nitrogen, basically the life cycle in soil, we realized that it's a very complex system. So even if we, for example, do some laboratory testing now, it would be kind of difficult to understand and calculate what the levels will be in the future by using deterministic methods. And that's what people have been trying to do for a very long time. Use some mathematical equations to determine, deterministically calculate, how much nitrogen will be in the soil at a certain time. But this is very difficult because the nitrogen assimilation and dynamics really are a very complex system that involves soil, the microbes, and the weather. And so we realized that we will not be able to probably make some measurements today and then put them into some formulas and then try to get the values out in the future. But let's take a step back and then look at the problem of today. So how can we measure soil nitrogen if we want to know the levels today? Well, one thing is that we want to make this as cheap as possible so that people use it. And lab testing is just not doing it. So we said, okay, well, can we come up with a point of use? And this would be the point of care equivalent for let's say, medical sensors. So can we come up with a point of use sensor toolkit that would allow us to measure soil ammonium and nitrate in the field inexpensively, so at low cost? And at that time in our lab, we had already developed a technology that would allow us to measure the ammonium levels in soil in the field inexpensively and so on, which I will talk about in a minute. But the problem that we were facing was, if we want to know the total nitrogen in the soil, we really need to know the levels of nitrate and ammonium. So ammonium we kind of have, but nitrate we didn't really have. And then we started looking into methods that would allow us to measure nitrate in soil in the field. And there are a few technologies out there, but generally they're expensive or fragile or not really reliable. So, and then, we tried to explore some methods ourselves, and then we realized that we are really kind of probably trying to swim against the current here. And that, we will not be able to probably come up with something that's gonna work as good as that we want and will be inexpensive. So that's the key parameter here. We want to do this cheaply so that it actually gets used. As I mentioned earlier, agriculture is a pretty cutthroat business and the margins are short. So the idea was then to, why don't we just drop this whole idea of measuring nitrate with a sensor? So can we actually try to model our system, and then so that we would be able to make predictions of levels of nitrate in soil using various parameters that could either be measured very easily or it already gets measured. So could we kind of eliminate the use of hardware and save money that way, and then put the burden, let's say, on computers and not on physical sensors in the lab. So, and the whole idea was, can we basically just measure the temperature and the rainfall and look at the time since fertilization, and then make a few other simple measurements? Well, we already know the levels of ammonium, and then we can measure the pH easily, and it already gets measured actually in many farms, and then soil conductivity. From these parameters, can we really create a statistical model, a machine learning model essentially, to be able to predict the levels of nitrate without using any physical sensors? So because again, at the end of the day, when we introduce a nitrogen fertilizer into soil, so whether it's ammonium nitrate or urea or whatever, it will always end up let's say, end up as soil ammonium or soil nitrate, nothing else pretty much. So that's kind of the idea. And then once we measure these parameters, can we then predict the levels of nitrate in soil without actually making a physical measurement using our model? And this is a statistical model, it's not a deterministic model at this stage. And then not only that, predict the levels of nitrate in soil right now, can we also try to predict the levels of soil ammonium and soil nitrate into the future? So that's kind of the idea behind our study, that try to eliminate hardware as much as possible, and then measure the things that are simple to measure, and then predict the things that are hard to measure. So that was really the whole concept behind our approach to this difficult problem. So as I mentioned earlier, when we started looking into this issue, to determine the levels of nitrogen in soil, we had already developed an ammonium sensor, and then we improved this a little bit, obviously, to make it a bit more high performance, a bit more selective. So what it really is that it's a gas phase measurement of soil ammonium, where a soil solution is introduced into a cartridge, and then we increase basically the pH of the soil, and then which releases the ammonium that's inside the soil solution into the headspace of this cartridge, where we have a paper-based disposable gas sensor. And the way this sensor really works is that there's always there's a layer of water that's around the cellulose fibers within paper, and then the conductivity of this layer of water is really quite sensitive to the water soluble gases that are in the environment. So in this scheme, the ammonium in soil gets converted to ammonia, and then which gets kind of released into the headspace when we increase the soil pH. So we push the equilibrium towards essentially ammonium to ammonia, and then some of it escapes. And then we have a little bit of sulfuric acid that's added to the cellulose paper, and then which basically acts as a scrubber, or sometimes I think what the term that's used is also a scavenger. So it really starts capturing the ammonium in the headspace. Ammonia in the headspace, and then and when the ammonia gets captured, the conductivity basically drops within paper as we neutralize the highly mobile protons within paper. So, and the gas sensors that we produce, they are very, very cheap. In our lab, they cost about 2 cents to make, And then at scale, we think that they will be probably about 10 to the minus 5 cents to make, very, very inexpensive, because they just consist of a piece of paper and a little bit of sulfuric acid. And here we have a wax barrier that's printed around the electrodes to basically confine the sulfuric acid additive to a specific zone within paper. So it really costs nothing, and they're very inexpensive to make in the lab. So and the way kind of these sensors again work is that once we add the soil sample to the cartridge, the conductivity of paper drops over time, and then we use this as the analytical signal. So once the change in signal drops to below a certain threshold, then we take the time it took to drop to that level as the analytical signal, and we could measure the ammonium levels in soil fairly accurately, and you know the performance of the sensors are high enough that they're actually useful. So they're sensitive and specific enough that that they're useful to measure soil ammonium. And again, because we're making the measurement in gas phase, we don't need to worry about matrix effects too much, because the gaseous matrix is a lot simpler than the solution matrix. I mean, if for those of you that never work with soil, it's a very complex matrix. There's all kinds of stuff in it, so it becomes very problematic when working in solution. So that's one of the reasons why we thought that our technology would actually be a real solution to this, to measure soil ammonium. So and when we compared our sensor to the external laboratory measurements, so these are the Bland Altman plots. There is so the data here is, so the mean is very, very similar. So there is only some couple of ppm difference in the measurement accuracy. So and we also don't see any large systematic bias in our measurements. So these are fairly reliable measurements that our low-cost sensor produced in comparison to the lab measurements. So again, we solved the ammonium problem of basically measuring soil ammonia in the field, so that we could eliminate the dependence on laboratory measurements. But once again, we still have this problem of nitrate. We don't know how much nitrate will be in soil after some time of adding the fertilizer. So and what we attempted to do once again is that predict the nitrate levels now and ammonium and nitrate levels into the future using machine learning. So before we could do this, we first had to collect data in our lab. So and this is to train our machine learning algorithms to be able to predict the levels of nitrate instantaneously, and nitrate and ammonium into the future. So and the way we ran the experiments is we basically took huge pots of soil, and then we added some fertilizer, and then we could then simulate rainfall by basically just watering our pots of soil, and then we could also modulate the temperature by wrapping around the pots of soil with nichrome wire. So and by turning basically by passing a current through these wires, we can then heat up the pots of soil to simulate various weather patterns. So and we basically simulated weather from very low rain, which is 1 millimeter per day, to tropical, which is 10 millimeters per day, and 10 millimeters per day is a lot of water. And then and temperature, we basically went from 20 centigrade, which is temperate, to 31 centigrade degrees, which is considered warm. So And then again, we have rainfall, temperature, and time since fertilization, in addition to ammonium levels, pH, and electrical conductivity that we could measure in the lab. And then in addition, we also took soil samples and sent them to an external lab for benchmarking and really generating training data, especially for nitrate levels, because again, we can't measure nitrate in the lab. So we collected some data, which I'm not gonna go over, obviously. And then we created our machine learning models. Again, it's just, these are all the details that are just not really that important at this stage, but please do reach out if you're interested in learning more about this stuff. But so we created our machine learning models. And then the good thing is that the machine learning tools, the software tools are fairly advanced nowadays and relatively easy to use too. So we were able to, using the XGBoost algorithm, we were able to use the, we're able to identify the important features in our classifier, and then assign weights to them. So it turns out that actually dryness is a really important predictor of how much nitrogen, nitrate will be in soil. And then the number of days have passed. This is also very important. And then the ammonium levels is an important predictor, temperature and rain, and etc. These are all important predictors of pH seems to be less, electrical conductivity seems to be similar to ammonium levels. But we created this machine learning model, and then by using our point of use, the sensor toolkit inputs. So really, I mean, the three things that we measured, which is electrical conductivity, pH, and ammonium levels, we were able to measure or predict the level of nitrate in soil with an R squared of 0.63. So, and again, here, please note that we don't really have a hardware sensor anymore. These are pure predictions. And these are really good results, especially when we consulted with the experts in the machine learning field. We were told that really anything above 0.6 is fairly good for such complex problems. So we were quite happy with this. But here, for example, there are many optimizations that one can make to improve the models. One would be to, for example, optimize it for different weather conditions. And the other thing is, that we can, for example, improve our sensors and so on too a little bit, especially our point of view sensors, because we have sparse data here too. But one thing that I also want to mention is, for example, if we go back a couple of slides, we measure rainfall and temperature, but we don't really measure soil dryness, which the external lab can do. But we can, again, using a machine learning algorithm, we could actually predict the soil dryness from the weather as well. So, and that means that we actually don't need to run additional experiments in the field to measure how dry the soil is. So, but anyway, so if we take the sensor data and then we tune our model to different weather conditions, we can actually, again, improve the performance. So, and then here, we were able to go up to about 0.7 of R squared equals 0.7. And again, the Bland-Altman plots show that there is obviously there is error. And but it's not really systematic in a way that that's very obvious across the board. So at slightly low, let's say slightly lower and slightly higher concentrations, our system seems to or let's say mid ranges and slightly higher concentrations, our system under predicts. And then at lower concentrations, it seems to over predict the levels comparison to the external lab measurements. And then if we actually improve the inputs, so we, instead of using our sensor inputs from that were generated in the lab, and then we replace it with high quality measurements of ammonium, electrical conductivity, and the and pH levels, actually our model performs much better. So that means that if we improve our prototypes, lab prototypes a little bit better, we can actually get an R squared of approximately 0.8, 0.85. Here we got 0.86 for the nitrate predictions. And that's very similar to hardware measurements. I mean, we were pretty amazed by the fact that just using software, we were able to measure the levels of nitrate in soil almost as accurately as some of the expensive tools that are out there. So which was very encouraging, really. And obviously, again, once the Bland-Altman plots show that there is some bias, obviously, at the lower, especially at the lower ranges and higher ranges of concentrations, but nothing that's systematic across the board. So so until now, I talked about really to make instantaneous predictions of levels of nitrate. But can we actually take a sample and then from this measure, predict the levels of nitrate for the same day, essentially for the same instant? And then from the nitrate measurements and the ammonium measurements on day 0, can we actually predict the levels into the future? And it turns out that for our system, again, these are lab experiments at the end of the day. These are controlled experiments. The field experiments would require much more data, and then they would require a lot more optimized and versatile models of the soil nitrogen. But in any case, so from measurements of ammonium and nitrate on day 1, can we predict the levels into the future? And then here we demonstrate that it is indeed possible to make predictions into the future. And here we were able to only do up to 12 days, as we didn't have a much bigger data sets for this study. And then we get an R squared of 0.64 for ammonium and 0.7 for nitrate. So do I have any time left? I think so. Basically, one last thing that I want to show you, which is a few minutes, is my students put together a video actually that kind of describes this technology and really defines the problem. All right. So, so finally, just to reiterate, I'm really excited about this work because it it basically checks the idea of whether it's possible to just measure the easy things that we can measure or already measuring in the world, and then predict the rest that are hard to measure. So that's kind of really what we try to do in this whole work. I'm out of time pretty much, so I will leave the slide. So I'd like to thank our sponsors, and also I would like to thank the organizers for putting together this amazing event, and then also inviting me. So I'm very grateful. And obviously, I would like to thank my lab that's done all the hard work. Last but not least, about our published work. So Arben Merkoci from your institution actually also wrote a commentary and news and views article about our approach to sensing in agriculture. So please do also check out his views on this topic. With that, I'd like to stop. Thank you very much for your time, and I apologize, I went over time, I think a few minutes.
Okay. Okay, thanks, Firat, for the nice presentation. So, is there any question here in the audience? Any question from people here? Not really. I think that in the chat. Oh yeah, Maria Jose. Yeah, please. Yeah. Do we have a? Wait, Anna.
Thank you very much for the nice talk. It's amazing, no? To use, I find it very, very interesting to use machine learning for prediction. So I congratulate you. So it's very, very nice. I have a question with respect to the electrodes for sensing ammonia. And my question is related more to the analytical parameters. Which is the limit of detection that you can get with these electrodes, and the other is what about the interference of other gases, like for instance CO2?
Yeah, so let's start with the limit. I mean, we were able to go down to a couple of essentially ppm of ammonium in soil. So and we think that we can actually improve this quite a bit. So we would even be able to go to ppb levels probably. But we would have so the way we kind of made these measurements, they could be more robust, essentially. For example, the analytical signal that we use, which is time passed, I don't think it's a very good way of doing it, actually. I think we can do probably a better job with, for example, looking at the gradients of the signal, etc., because it's a time series signal that the sensor generates. Or we can again use machine learning type of algorithms to improve the signal. So, but it's in the ppm range, essentially, single digits of ppm. That's where the cutoff is. And in terms of the interferences, so CO2 is not really a big problem in this case, because the sensor that we use, it's already very acidic, and the solubility of CO2 just basically is very, very poor. Even without any additives in our paper, we could only measure, or it's only sensitive to levels of CO2 that's upwards of a couple of %, because just CO2 is not very water soluble. It has a low Henry's law constant compared to ammonia, which has one of the highest. And then, but on top of it, we even make the paper acidic to make it more selective towards ammonium or ammonia, and less, which is more of an alkaline gas, for the lack of a better term. But for carbon dioxide is acidic, so it really doesn't dissolve too well in the paper sensor. So matrix effects, they are definitely an issue, but it's way less of an issue if, for example, we were to make these measurements in solution, where you have all kinds of different things, because the composition of the headspace is just very simple, and there are just not too many species that would interfere with this measurement, basically. I hope my question was clear. my answer was clear, sorry.
Yeah, okay. I think we are really running out of time, so I think it's time to move. Thanks, Firat, for the nice presentation. Thank you.
Thank you very much.